So I think we're live now, so I can start this presentation. Okay, hello everyone. My name is Amir Alhoj, and I'll be the host of today's presentation. Today's presenter is my friend and colleague Tahir Kubana, and we are both members of Young Professional Affinity Group Executive Committee in Bosnia and Herzegovina. We are extremely proud and honored to take part in this IEEE Connecting Experts program. And today's topic is artificial intelligence-based protection of microgrids. Of course, during the presentation, everyone is allowed to ask any questions on all of our social media platforms, and Tarek is going to answer it afterwards. Also, for those who will watch this video after today's live stream, they can send us their questions on our social media platforms, and I will try to answer it as soon as possible, of course. So without any further ado, I think we will cover all these basics. So please welcome today's presenter Tarek Kubana.
Okay, thank you, Emir. I hope you can clearly hear me and see me. My name is Tarek Kubana, and today we will talk about the artificial intelligence-based protection of microgrids. First, let me introduce myself. As I already said, my name is Tarek Kubana, and currently I work as an expert associate at Elektroprivreda of Bosnia and Herzegovina in Sarajevo, in the capital of Bosnia and Herzegovina. That is actually our largest distribution system operator public company. I finished my bachelor and master degree here at the University of Sarajevo, and I obtained my PhD and the title of Doctor of Technical Sciences at the Technical University of Graz in Austria. So throughout my work, my professional work, and my academic and research work, I've done a lot of research around the distribution systems, and I saw microgrids as one of the emerging concepts that will be interesting in the near future, and therefore a lot of my papers are about the subject of the microgrids. So today we will start this presentation. I would like once again to greet you all, and let's start. So in order to have a clear picture what a microgrid is and how did we evolutionary arrive at the point where we have microgrids, we need to start from the beginning. So we all know that electricity is a unique commodity because it cannot be stored and it is highly influenced by other commodities, and demand and pricing depends on the season and daytime. So electricity needs to be supplied immediately. Unlike any other commodity like oil crops or metals, the delivery period for electricity is equal to 0. When it comes to the history of making the electricity, which will be important for our later talk, in 1882, Thomas Edison achieved his vision of a full-scale central power station with a system of conductors to distribute electricity to the end users of the high-profile business district in New York City. So at that point, that first grid, that small grid, served an initial load of 400 lamps with 82 customers. So just 2 years later, it was serving 508 customers with around 10,000 lamps. So this was some kind of the local-based small power grid. Throughout the history, these grids grew in size. So we arrived at today's point where we have a large-scale thermal power plants, large hydropower plants, nuclear power plants, and finally renewables like wind and solar. So throughout the history, the interconnections were made. Throughout the history, first each country or smaller parts of the system were operated by the system operator. As we can see here on the right-hand side, we had these number of different power plants, like hydro power plants, wind power plants, solar, nuclear, and thermal power plants operated by the system operator, and they helped to distribute the energy to the industry, households, and railways. With the growth of the population and with the growth of the electricity grids, different system operators were established in different countries, but they worked independently from each other. However, they started to interconnect into larger power systems, and therefore we arrived at the point that we have today, and that is the point where we have large interconnections. So we are part here in Bosnia and Herzegovina and the larger part of Europe, we are part of the European interconnection. And by definition, the electrical network where voltage and frequency do not depend on the size of the connected load is called a large-scale power system. So when we talk about these large-scale power systems, they distribute large amounts of energy. But how does these amounts of energy arrive to our homes? So the traditional power grid that is common in all parts of the world is shown on this slide here. So we have a power station, any of these sources I mentioned before, which can generate electricity. We have a substation transformers, which raise the voltages of the electricity for the efficient transportation. We have transmission networks, these large poles that transport electricity over long distances. And then at the places where we need to consume the energy, we have the substation transformers that lower these voltages. And finally, we have distribution lines that distribute this electricity to our homes. And in the end, we have the consumers, which are homes and businesses. So with the advancement of the technology, of the information systems, of the communication, our grid started to be smarter. So what is actually, we all the time we hear this term smart grid. So the smart grid is the modernized electrical grid, a transmission and distribution infrastructure that is reliable, both reliable and secure, and can meet future demand growth, but while intelligently responding to the behavior and actions of all the electric power users connected to it. So now, today, in our grids, we don't have just these wires and cables that supply our energy. We have a lot of intelligent devices in our grids. We have automated reclosers, we have smart meters, we have large SCADA systems that help operators to control the grid, and all different kinds of electronic protection devices and algorithms that help these grids to be resilient and efficient. So if we take a look at the traditional grid that is shown on this slide here, traditionally we had a utility grid and over a substation transformer that we showed on the previous slide, we have commercial and industrial consumers and residential consumers. And the energy flow was unidirectional from left to the right in our case. In the past couple of decades, at these distribution levels, distributed generation kicked in. So now it is common to have solar power plants on our roofs. It is common to have small wind power plants and different kinds of renewables in our distribution networks. This, of course, changes a lot of properties of our distribution networks. So we have these renewables that are installed. Also, the electric vehicles, even though they seem like a simple component in our grids, they are not, because they are quite large consumers compared to the residential homes. And they can be also used to provide energy back to the grid in the cases that we have their batteries full. And finally, we have different kinds of energy storage systems that are with every year becoming cheaper, and we will definitely see them more in our distribution networks. So all of these different devices, concepts are changing the flow of energy in our system, and therefore we need different intelligent electronic devices that will control the load flows and help the operation of our grid. So what are the actual geopolitical drivers to use smart grids? It is the global energy demand, which is constantly growing, and it is expected to grow by 100% by 2030. Greenhouse gases emissions are also one of the concerns because 40% of them are accounted for the electricity generation. And of course, a separate story of energy efficiency, where the cost of generating a kilowatt hour versus a cost of saving a kilowatt hour through efficiency is by 170 times fold. So by incorporating all of these strategies, we see why smart grids and future investments in these intelligent networks are important. So then what are microgrids? So with the constant increase of installed DG power, distributed generation, especially in our low voltage networks, which are actually the grids around our neighborhoods, we arrive at the level where these local resources have enough power to supply the local consumers. And this means that our local solar power plants, wind power plants, electric cars, energy storages may have enough energy that the energy exchange between that part of the system and the distribution network is reduced to minimum or also or close to zero. So this ability to ensure supply of the local consumers, even in the cases of outages on the primary grid, can lead to these grids to switch to islanded mode of operation, of course with an appropriate equipment. And these grids that can switch to islanded mode and grid connected mode are called microgrids. So by definition, a microgrid is a group of interconnected loads and distributed energy resources within clearly defined electrical boundaries that act as a single controllable entity with respect to the grid. So what does it mean? This means that one part of the grid, which is called a microgrid, can be controlled as a single entity from the respect of the grid, as shown on this upper left part of this picture. So here we have a microgrid that is part of the larger grid. This microgrid, since it incorporates a lot of energy storage devices and a lot of distributed generation, it could store excess energy, for example, just like a large battery. Or this microgrid could provide energy when needed, like a power plant. So also, a microgrid could be used to balance out fluctuations in the grid voltage or frequency. So imagine a scenario where we have a large number of these microgrids in our system that can work both grid connected and in islanded mode. In the end, this grid would be resilient and we would almost eliminate outages that may happen to the grid. So now let's go back to the smart grid that we explained earlier. In order to control all of these different entities in the microgrid, we need to have a microgrid controller. So see, here we have this microprocessor-based electronic device that has a large number of inputs and controls these different entities within the microgrid. With this type of control, the grid can switch between grid connected mode and islanded mode of operation. So here we see the grid connected mode where the energy is supplied from the utility grid. In the scenario where we have enough energy within the microgrid, we can go in the islanded mode of operation. So this means that if a fault occurs at the primary utility grid, this microgrid can go totally in the islanded mode and be resilient and have energy supplied to its local consumers. So what does it mean? We can see here on this slide where we have the utility grid and a couple of microgrids that are connected in a radial manner, which is a common in a distribution systems. So let's say a fault occurs at this part of the line with the traditional distribution grid with the radial feeders. all lower parts of the feeders would stay without electricity until this fault is cleared. But in the case of the microgrids, considering that all of these island mode of operation, only this part, only the line or the cable with the fault can be taken out of the system, and all consumers will have their energy supplied. So what are the most common microgrid components? In order to work, microgrids must include three essential components. First one is of course the locally produced energy to ensure they can operate independently in any event when they are disconnected from the main grid. So this means a lot of renewables, batteries, or even some kind of the generators in the last case. Storage systems are important part of the microgrid because they can store the excess energy and used to balance these grids in the island mode of operation. So currently, these technology of batteries is becoming cheaper year by year, and we will definitely see them installed in our grids. And finally, a smart management system to ensure the continuous balance between electricity generation and demand. But where do we use these microgrids today? Today, they are almost exclusively reserved for a couple of applications. So first one is the remote off-grid microgrids. As you may think, these are the islands, actually, offshore grids. So due to the economic issues or their unfavorable geographic locations, it is impossible sometimes to connect these regions to a public power supply, and therefore the microgrids are installed there, and therefore they constantly work in the islanded mode of operation. Another important aspect and application of microgrids is the military microgrids. Of course, a reliable network is crucial for the physical and cybersecurity of the military operation, and therefore military creates microgrids so the troops are not dependent on the public power supply. And finally, the industrial microgrids, because for some production processes, interruptions to the power supply or a very long startup time can result directly in high losses or of revenue, and therefore it is feasible to install microgrids in these kinds of systems. So, but here, these are some specific cases. What is interesting to us as the end consumers, as engineers, and as distribution system operators are the microgrids that are installed in our current low voltage or medium voltage networks. So in order to evaluate whether that investment into microgrids is feasible or not, several aspects need to be considered. So the benefits that result from the setting up of a microgrid from the existing low voltage network come from the ability of the isolated operation of this entity after interruption of the upstream network. So in this case, most of the microgrids are built upon existing electrical infrastructure, which will actually help to reduce the overall cost. So if any on-site generation is already present, which may be the case in the upcoming decade, where almost every neighborhood will have some kind of renewable or distributed generation installed in the system, then this grid infrastructure and protection and automation investments can be significantly reduced. So the microgrid, what are the microgrid benefits? When you consider a microgrid, you need to assess several benefits because you cannot only look at the one side. So stakeholders in the microgrids are consumers, producers with their microgeneration, and the distribution system operators. When it comes to the consumers, their energy bills can be reduced by the usage of microgrids, and they can have increased reliability because of the higher reliability of the microgrids. From the point of the micro generators, the benefits can be seen in the additional revenue from the potential extra energy selling during these times of islanded mode of operation. And from the distribution operator point of view, the benefits include improvement in global reliability indices, which are actually the measures that are assessed by the DSOs, and they can avoid penalties or earn rewards from the regulator, depending on the regulation and the country where the microgrid will be installed, and avoid penalties that are paid directly to the customers. In order to evaluate whether a microgrid would be feasible to install, when I say we, I mean me and my colleagues who did this research, tried to assess a willingness to pay for reliable electricity, because if the consumers want to be part of the microgrid, they may have wanted to pay for a higher energy price in order to have a higher reliability in return. So to do this, we did a contingent valuation study here in Bosnia and Herzegovina. Regulations are imposed upon the power distribution system operators, and these regulations sometimes cannot be met by the DSOs unless the consumers go in with the increased prices. So this means that the power quality and reliability levels when I speak about the European distribution system operators are often brought to the margin where additional investments are just not feasible. And in order to have a more reliable supply, consumers can pay and will have to pay to have an improved service. So this is one of the aspects when it comes to the microgrids. So in order to have a microgrid where your residential or business entity is located, you may have to pay for a higher electricity price. And this is actually what this research wanted to investigate. The contingent valuation method is actually a widely used method for estimating economic values for different kinds of services and goods which are not traded in the market and therefore have no market price. This method is applied through conducting a survey in which people are directly asked, so how much would they pay? So how much would they be willing to pay for a specific service? Also, on the other hand, it is possible to ask through that survey the amount of compensation or willingness to accept in order to give up some services. By evaluating these two values, willingness to pay and willingness to accept, it is actually possible to evaluate the price of that service. So here we wanted to evaluate the amount of money a household is willing to pay for a specific level of service. So the estimated willingness to pay can be compared with the incremental costs of achieving improvements, which as a part of service provider business planning and regulator decision-making process may be important. So since the electricity consumers are unable to accurately estimate the costs, these consumer groups were asked two important questions among different questions in this survey. So the first one was how much would you be willing to pay for electric service to avoid the power interruption in the case of the interruption, which is used to evaluate the willingness to pay, and how much would you accept as a credit for the particular interruption scenario, which is actually the willingness to accept. In this survey, 364 domestic consumer respondents were assessed and with their different habits about consumption of the electricity. So after that, the model for willingness to pay for domestic consumers is set up, where three important predictors were selected, and these are electric heating, employment, and time spent at home. On the other hand, 72 companies were also part of this survey, and four different predictors variables were used to evaluate, to create the model for them, and that is the size of the enterprise, the sector of activity, the backup system, and monthly bill for electricity. And here are the results. So for the domestic consumers, these socio-economical parameters can be ranked in the following way. So which one is more important, and which one affects more the willingness to pay for higher electricity price? And that would be electric heating, employment, and time spent in the house. On the other hand, when it comes to the business consumers, 55% of enterprises use some kind of the backup power. They have some kind of the UPS system. And the model that describes the behavior of this variable with the business consumers is presented here. And here we see that the electricity bill is actually the most important predictor of the model when it comes to the business consumers. So also business consumers are much more willing to pay for the reliable energy because of the higher returns compared to the domestic consumers. So to conclude this part of the research, business consumers are willing to pay more because they are more affected by the interruption. And the average willingness to pay of the domestic consumers for avoiding 1 hour interruption was estimated around 3 Bosnian marks, which is around €1.5. And the average willingness to pay of the business consumers is assessed around 105 Bosnian marks, which is around 52 euros. So this information of how much different consumers are willing to pay can be used to assess the economic efficiency in the setting up of the microgrid at one part of the system. Another part of the story is that most of the business consumers want to have a green footprint, and they won't have their energy to be entirely supplied from the green energy sources. And in that cases, the distribution system operator needs to have green energy in the backup as well, which is actually the scenario that microgrid enables. We already talked about different challenges in the microgrids, and we told that the control of the microgrid is one big part of the problem. But another more sensitive part of the microgrid challenge is the microgrid protection, since it comes to the safety of the operation and the safety of the people and the personnel in that part of the system. So when it comes to the microgrid protection, there are 5 characteristic technical challenges in the microgrid protection. So these are the blinding of protection, the false sympathetic tripping, the recloser problems, the changes in the short circuit level, and the unsynchronized reclosing. So we will go briefly through each and any one of these. So blinding of protection. Here we can see a standard substation with 2 radial feeders. When you have a distributed generator installed in the system, in the case of the fault on the right side of this generator, both generator and the main grid can contribute to the grid, and therefore it can lead to the blinding of the protection, where this fault relay measures a lower current than the actual fault current. Another problem is false or sympathetic tripping, because the distributed generator again contributes to the fault, and the fault current flows both from the utility grid and from the distributed generator, and there is a possibility of a relay to trip due to the upstream current. Next one are the problems with the reclosers in the scenarios where we have reclosers and diffusers in our system. So in a scenario showed here, we see the fault on the right side of this fuse, and by contributing to the fault current by this distributed generator, the fuse current may be higher than its working current, and it may operate faster than this recloser. And of course, the constant changes in the short circuit level, which are happening all the time in the case we have a microgrid, because when these microgrids are working in the island mode of operation, especially in the island mode of operation, different short circuit levels that occur with the changes of the production of different renewable sources in the microgrid will lead to changes, and that will show a need for adaptive relays because these fault currents won't be the same all the time. Another one is also unsynchronized recloser. Reclosing, it is the scenario where DG keeps the disconnected feeder energized, which actually may be dangerous for the crews that are outside and solving these faults. Of course, all of these problems can be solved. We have the technology to solve these problems. We have the relays. We can protect the microgrid with the technology that we have today. Existing techniques that are actually answer to these previous problems are adaptive protection, voltage-based methodologies, differential protection, distance protection, overcurrent protection, and techniques with external devices utilization. However, all of these methods, although they perfectly can solve the problem, are just not feasible to be used on the low voltage or medium voltage levels. So these expensive relays are commonly used in the high voltage levels, where it is perfectly reasonable to use these devices. Therefore, this was the motivation for the next couple of researches that we were doing that are actually based on the artificial intelligence. So throughout the last couple of decades, the artificial intelligence was the fantasy, is the fantasy of many scientists and engineers, and we as engineers are trying to incorporate this artificial intelligence and try to solve problems that we couldn't with other techniques. So with the advances of technology, computers started to learn and to solve problems. And if you think back to all these smart grids, all the data that we are collecting, microgrid controllers, and all these intelligent devices that we do have in the system, as a result, we have a lot of data. And artificial intelligence actually likes data and can use this data to produce some useful outputs, especially during the power system failures. In these cases, the system starts to behave dynamically, and by obtaining data in this time, we can make some smarter decisions. So also in the near history, we will see a shift from the traditional distribution system to microgrids, as we explained earlier. And in the part where the microgrids start to work in the islanded mode of operation, a redesign of the protection strategies may be needed. So currently, protection devices already use some kind of microprocessor-based relays or industrial computers, and it would be a natural upgrade to the existing protection schemes to implement some kind of the artificial intelligence-based algorithm. So we will go shortly through the background of artificial neural networks and different pre-processing techniques that we used in order to implement these algorithms. So artificial neural networks, as most of us know, are based on the biological neural networks when they mimic a large number of nerve cells that work massively in parallel and have the capability to learn. So there is no need to explicitly program a neural network, and they are able to generalize and associate data, and they can find solutions for similar problems that were not explicitly trained. On the right side, we see a standard artificial neural network structure. One interesting approach that was used into these researches is Hilbert-Hwang transform. We tried to use a Fourier transform, a fast Fourier transform, which is common for measuring harmonics, especially according to the EN 5160 standard here in Europe. But the time for measuring harmonics and for calculating them may be too long in order to use them efficiently in the protection terms. So an interesting concept we tried is to use the Hilbert-Hwang transform, which is actually, in short, a way to decompose a signal into intrinsic mode functions and obtain instantaneous frequency, and it is made up of two parts. So first one is to get the IMF by handling signals with the EMD, empirical mode decomposition, and the second one is to get the time frequency spectrum by handling these IMFs with Hilbert spectral analysis. Also, in this research, we used a wavelet transform for the pre-processing of the data. Wavelet analysis is performed in the time scale region. So a bigger time window is required to catch low frequency and smaller window to catch the high frequency components, which is actually one of the benefits of these transforms, which is a wavelet scaling. So they are very useful because they capture both frequency and location information. However, since we speak about digital signals, digital data, we will use discrete wavelet transform, of course, which is actually any wavelet transform for which the wavelets are discretely sampled. And on the right-hand side, we see a number of high-pass and low-pass filters that are used to filter these basic signals in order to obtain different details and approximations of the system, of the signal. Here we see a traditional distribution network. Again, now we are speaking precisely in the terms of the medium voltage distribution networks. So the typical, this is a typical topology. This typical network throughout the history did not have distributed generation, so we didn't have in-feed from the grid. In the modern time, of course, renewables showed up. Now we have these DGs in our system, and these load flows within the system are currently changing. And finally, with the disconnection of this grid at the place of the common coupling, which is here on these circuit breakers, these kinds of networks can go into islanded mode of operation and work as a microgrid. So now I will present you 4 different methodologies that were used to improve the protection strategies of the microgrids by using artificial intelligence and some kind of the pre-processing technique coupled with artificial neural networks. So the first one was HHT-ANN algorithm, which stands for the Hilbert-Hwang transform artificial neural network algorithm. So for this research, a part of the real power distribution system is developed, which we can see on the right-hand side. We measured voltages in the bus number 2, and we had variable fault location at this line number 1. So with the variable fault locations and the fault resistances, 3 different types of faults were simulated and the voltages were measured. These measured voltages are processed with the HHT according to the diagram shown in the right-hand side. So by obtaining these IMFs are coupled together to create a so-called signature signal, which will actually be used to reflect each and any fault scenario in the system. 180 fault scenarios were simulated, and this is the method that was used. So we measured voltages at the bus number 2. We pre-processed these 3-phase voltages with the HHT. We coupled them together into one ANN input vector in order to create the signature vector for each fault scenario, and then we trained our network. The network training was done according to the algorithm shown in the right-hand side. So we did some simulations, we measured voltages, we pre-processed these voltages, we obtained IMFs, we created the signal. After that, the learning process of the neural network was initiated with expected outputs for 3 types of faults and no fault. And we had our fault detection and classification algorithm ready. So once we trained this network, now we can use it in the same manner in a real power system in order to evaluate, did the fault happen and which type of fault happened. Here in this table, you see 5 different test cases with different fault resistances and fault locations and fault types, and we can see that the mean squared error for this classifier is less than 1%, which is actually great. However, when it comes to these IMFs that we explained earlier, the number of IMFs that can occur in a signal can vary. So this means that the important information can be hidden in the higher order IMFs. And the more suitable algorithm for the extraction of the valuable information during the fault was necessary. This led to the DWT signal decomposition. So the next methodology is DWT, discrete value transform artificial neural network algorithm. So the faults are simulated for the different fault resistances and different fault locations. Again, the system showed at the right, and 3 different fault types were simulated. Now we had 1,600 fault scenarios. The method for creating the signal was more or less the same with the HHD pre-processing method. So we calculated different details and approximations by using the DWT, and we obtained again a signature vector, which is shown here on the right side. Here you see this signature signal, this vector that actually reflects each operation scenario of this grid. On the right side, you see the methodology. So again, the voltages were measured, pre-processed with DWT. 5 different approximations and details were obtained, and these signals were actually glued up together, concatenated together in order to have this signature signal. So again, the created signals are inputs to the neural networks. The neural networks is trained with the previous known outputs from the simulation, and once trained network can be used in the same manner as the previous one to detect the fault and classify different fault types. Again, with the 5 different test scenarios, we see that the accuracy is great because the mean squared error is again less than 1%. So motivated by the capability of these previously presented algorithms in terms of high impedance fault detection, because we saw that the faults can have a couple of hundred of ohms in the fault resistance, which is actually the scenario that occurs in the microgrid when the microgrid works in the islanded mode of operation. Because it is not connected to the primary grid, the short circuit levels are low and the resistances of the fault are quite high. So the microgrid protection, as we previously presented, is still a challenge, and these 2 researchers led to an assumption that these methodologies could be used in the islanded mode where the fault currents are significantly lower. So the next algorithm will be a microgrid DWT ANN algorithm. So now both grid connected and the islanded mode of operation in the same part of the network were simulated. The fault locations are shown here on this line number 1 and this feeder number 1. So again, 3 fault types were simulated, different locations and resistances, and now we used the white noise with the value from 30 to 50 decibels that was added in the signal measurements, and it resulted in almost 90,000 simulation scenarios. Again, These simulation scenarios showed great accuracy with different fault resistances, fault locations, and different fault types, with the mean squared error less than 1% for the 50 decibel noise. Of course, with the increase of the noise, the accuracy decreases. So the accuracy improves with the noise reduction, of course, and we have 96.92% for the signal to noise ratio of 40 decibels and over 99.9% for the signal to noise ratio of 50 decibels, which actually implies that the noise levels in the measured signals are important. So the measurement in the bus bar we presented in this research ensures satisfactory fault detection, but it does not detect the faulty feeder. These tests also did not include the abrupt changes in the systems, like the load changes, switching off large consumers, capacitors, or faults in different feeders, which meant that the robustness of this method should be improved. All of these assumptions actually led to the final research, which is actually ANN-based station protection. Station protection is usually a term used for the full functionalities of the protection of your substations. So in this research, I tried to incorporate all of the standard station protection features by using these presented methodologies. So again, now we measure both voltages and currents, which is common in all secondary and primary substations. The faults were simulated over various fault resistances and locations, now with 3 feeders and different locations. Each simulation has different loads and DG power outputs that are actually set according to the daily load curve in this part of the system. And different levels of noise are added in the range from 21.94 to 50 decibels of signal to noise ratio. Actually, this 21.94 is the marginal value according to the EN 50160 standard, which states that the harmonics, which states the level of the harmonics that should appear in the medium voltage networks. And the moving time frame for capturing this data was analyzed, since it changed from 30 to 100 milliseconds. All of these different assumptions, all of these different scenarios led to the total number of almost 2.5 million simulation scenarios. And now let's see the results. So the feeder selection algorithm, which is an improved algorithm besides this detection and classification algorithm, takes the pre-processed feeder currents as inputs and has 2 possible inputs: fault occurred in that feeder or fault did not occur in that feeder. On the right side, we see how this algorithm for the feeder isolation works. Again, we pre-process these signals with the DWT in the same manner like the voltages. And once trained, this algorithm can be used in order to detect the faulty feeder in our part of the system. Another functionality that was added was the fault location algorithm, because it is extremely important in the distribution system operator regular work to know the exact fault location in order to quickly repair the fault and continue with the supply. This algorithm actually used current measurements, again pre-process them with the DWT signal pre-processing, and now having the different output, since this wasn't a classification problem for the neural networks, and the outputs were in range for 100 to 100, from 0 to 100% of the line length, where the percentage indicated at which place the fault occurred. So after implementing all of these functionalities, this algorithm should be able to detect the fault, classify the fault type, isolate the faulty feeder, and estimate the fault location. And let's see the results. So for the grid-connected mode of operation, we had a maximum error of 17%, and of course, this error decreased with the decrease of the noise. In the islanded mode of operation, this error was somewhat lower, around 8%, for this maximum allowed value of the signal to noise ratio. When it comes to the faulty feeder detection algorithm, in the grid connected mode, the error was maximum error was around 8%, and in the island mode of operation, maximum error was around 5%. Again, it decreased with the decrease of the noise. And finally, for the fault location algorithm, on the left side, we see errors for 3 types of faults, since in this case, the accuracy did not depend on the level of the noise. And we see that the worst accuracy is below 0.1% for the single line to ground faults. And on the right-hand side, we see how the moving time frame size affects the accuracy as well. So basically, with the larger moving time frame, the accuracy increases, which means that we have more data and that the neural networks are capable to assess these data better. However, we do need to make compromise if we want to have a fast reaction and a lower reaction time. So finally, to sum all this up, the appropriate microgrid protection still presents a challenge, and it will remain a hot topic for the researchers in the next couple of years. This presented work demonstrated the applicability of artificial neural network-based algorithms, and over the years, the results of research and new fundings led to this DWT preprocessed data coupled with artificial neural networks. And since microgrids mainly rely on the utilization of the renewable DGs, there are direct environmental benefits and economical benefits that come with the increased use of the microgrids, as we presented at the beginning of this webinar. Of course, the requirements for the reliability of supply are higher than ever, and more regulations are imposed by the regulator, which DSOs struggle to achieve, and especially because the infeasibility of these investments. And we showed also that if the consumers are willing to pay for the increased reliability, these requirements could be achieved, and the consumers, in the most cases, actually are willing to pay for the increased reliability. In the end, the presented results of this couple of researchers presented the practicability of these protection algorithms in terms of fault detection, fault type classification, faulty feeder detection, and fault location estimation. The robustness of the algorithm is achieved with all kinds of variations, which may actually occur in the real system as well, in these different simulation scenarios, where we have almost 2.5 million simulation scenarios. Of course, this research doesn't stop. So the future research direction should include the robustness improvements and validation of the algorithm on multiple real microgrids, because there are still some corner cases that may occur during the system operation that may lead to the false fault estimation. And one important part of the problem are significant changes in the network topology, which are actually common in distribution systems, and they can lead to the false estimation due to the significant change in the system parameters, but this could be solved by additional training to all possible network configurations that may occur in that part of the microgrid. Okay, thank you very much for your attention. I hope you have some questions. My colleague Emir will moderate now this Q&A session.
Okay, Tarek, thank you. This was like 45 fast minutes well spent for today, really. And I can imagine how much hard work you invest in this researches, and you're really a role model for all of us. So for questions, I I do have one participant that raise his hand, so I will allow him to talk. So hello, Mohammed. You can ask your question. I am unmute you right now.
Thank you for your great presentation. Alhamdulillah, it was very interesting and it was very catchy, and it's very futuristic. I appreciate your efforts and hard work. So my question is, like, in the end of the presentation you mentioned, because throughout the presentation I have seen, because you have you have only one transformer, like couple of two transformer in the feeder side, and you have multiple lines, and
Yes.
multiple loads. So because you have done the space, this all research and all methodologies and training everything for these lines and loads, right? So if I change the bus numbers or load numbers and or node numbers, the training system will change. Is it true?
No, actually, it is part of the same training, and I will go back to that slide.
Because these four factors which you mentioned, because it will be based on the training. So now, because the training procedure the steps will be same, but the methodology may change. Am I right?
Actually, there are three different methodologies here. The first
Okay.
one is used to detect the fault and classify the fault type. The second one is used to detect the faulty feeder, and the third one is used for each of these feeders to estimate the fault location. So when each of these methodologies is used, it actually goes to number of cases which methodology were used for each case. For example, the fault happens in the system. The number one algorithm detects the fault and classifies the fault type. The number two algorithm detects the faulty feeder. And now we have a number of algorithms for each of these feeders, which evaluates the fault location. So actually, yes, we do have number of trained networks and the number of methodologies that are used depending on the fault case in the system.
Yeah, like, if because it is a radial feeder, this is radial feeder, so you are having
Yes.
specific like 35 kV from the input, and you are going to multiple loads for in the radial manner. But in the ring type networks or different nodes, like in a standard 13 by 13 bus IEEE system, or like 9 bus for the distribution system side. So in
Yes.
the radial ring type feeders, then it will be the training system we may change. Am I right?
Yes, of course, of course. Each microgrid should be trained by its own training system. So
Hmm.
it is not unified for all types of microgrids. And therefore, I use this because in this part of the Europe, almost 90% of these networks are radial type. And actually, there are slow, really low number of cases where we do have connected
Hmm.
ring types of
Hmm.
the feeders, except in the very large cities. But the
Okay.
algorithm showed its practicality on the number of changing parameters, and the new network could be changed also, could be trained also to that type of the problem. And I don't think it would be actually a problem for this methodology to deal with that.
Yeah, I have a last question. Like,
Okay.
because as you mentioned that you are doing for a specific region, like European countries, you have selected. So because maybe based on the frequency and based on the voltage levels, or from you have taken 35 to like all type of loads. So if you consider the GCC countries, like Arabian countries, the Arabian
Okay.
Peninsular, so it has different space, like load kinds and features and load profiles. So I'm hoping it will be different from the Western countries and Middle East countries and Asian countries. Is it true? How do you
Actually,
see?
actually, when it comes to the load type, this system is changed for each specific point on
Hmm.
the daily load curve. So
Okay.
it is not trained to the specific type of the load curve, then for the
Hmm.
each point of the load curve. Therefore, it wouldn't be a problem to train the algorithm for any type of the load curve. I just used the load curve from our country, in order to achieve robustness and to prove that it will work in all different points of operation of the system.
So if you are training on the each point, then how will you ensure the peak shaving, load leveling, and load shifting and peak shifting? Will you able to do the perform all these operations here? If you do, like, change them. If you are able, if you want to do the peak shifting, load shifting, or load leveling in your microgrid system, simultaneously you want to provide a short circuit for that system. Both are possible, or maybe you need to isolate them. And
yeah, actually, the more specific scenarios you recognize in advance, the better your training will be. And actually, when you think about the protection, a couple of days or week of pre-processing and training is nothing when you compare it to the working algorithm that you will install later. So when you want to apply this algorithm to one specific part of the network, you as a protection engineer should know all the parameters and the possible scenarios that may occur in this part of the network. And this learning procedure is totally automatized. It is developed in the MATLAB code. So you just put different parameters, your corner cases, you put number of simulation scenarios. You do want, of course, you need to take care of not overfitting with this neural network. And after hours or days of learning, in the end, you will have algorithm that is perfectly suitable for your network.
thank you for your great explanation, and alhamdulillah, I benefited a lot. So in the future, if I have any questions, I may email you, and I will be in touch with you.
Yeah,
Hope
of course,
it will be fine. Yes. Yeah.
Feel
Thank you.
free to contact me.
Yeah. Thank you, Tariq. Thank you.
Thank you for your great questions. Really good technical questions.
Okay, Tariq, I think that's it. I don't see any raised hands or any question that we got on our social media platforms and here in Zoom application. So I think for today, that's it. If there is anyone that would like to ask anything, you can raise your hand now. And if don't, I think that we're finished for today. In the end, I would like really to thank everyone for listening, and thank you, Tariq, for this wonderful presentation. I really enjoyed, and I think the more people see this, the more this area of science and protection in general will be improved. So goodbye, everyone, and I wish you have a nice evening. Thank you.
Thank you, Emir, and thank you, everyone, for your attention. Goodbye.